Now for rigid body motion, we can use a similar set of equations as we did for particle kinematics. So let's say we have a coordinate frame X and Y, and we have a rigid body here. We'll say this is point A, this is point B, both on the rigid body. Then the vector position of A is RA. Position of B is RB. And position of B with respect to A is RB with respect to A. So from the vector addition, we know RB equals RA plus RB with respect to A. So if A is moving, and then B will also probably be moving. So this part is the translational. This part, how B is moving with respect to A, is the rotational. Formulas for translation. So we've got position, velocity, and acceleration. And then we'll have rotation. So for both of them, radius B equals RA plus RB with respect to A. Then for velocity, this is going to be VB equals VA. This one is going to be VB equals VB with respect to A equals omega cross RB with respect to A. Because different components of these derivatives goes to 0. Now for acceleration, AB equals AA. And then for acceleration for fixed axis rotation, AB equals omega cross R plus alpha cross R. This is the cross product, so it makes a vector. That R is B with respect to A, and the omega is of member AB, and also the alpha, which is angular acceleration, is of member AB. Now for fixed axis rotation, we know that in scalar form, if a wheel is rotating with speed omega and it has radius r, then the velocity of a point on the end of the wheel, which is going to be tangent, so 90 degrees perpendicular. The scalar formula is V equals R omega. Now we know that S equals R theta. Say that's theta, that's S equals R theta. V equals R omega. So then the scalar form of A equals R alpha. So we can relate translational to rotational using the radius. So position, velocity, acceleration. The same fundamental differential relationships that we had for translation. V equals ds dt, A equals d squared s dt squared equals dv dt equals dv ds times v. We had these four for translation. We can also write these for rotation in the angular form. Omega equals d theta dt, alpha equals d squared theta dt squared equals d omega dt equals d omega d theta times omega. So just separate and integrate as before to solve for some of the problem, like some of the variables given other variables. Now, if acceleration equals constant, then we'll get omega equals omega initial plus alpha t, theta equals theta initial plus omega initial t plus 1/2 alpha t squared, and omega squared equals omega initial squared plus 2 times alpha times theta minus theta initial. So that was for rotation. And this looks really similar to the ones we had for translation, which were similar to the projectile motion equations. V equals V initial plus AT, S equals S initial plus V initial T plus 1/2 AT squared, and then V squared minus V initial squared equals 2 times A times S minus S initial. So that is for constant acceleration. This is translation, which we have covered before, and this is rotation, which we are covering now. So you remember to get these equations from the differential relationships, you just separate and integrate. Quick example for V equals ds dt, we get ds equals V dt. We integrate S minus S initial equals Vt. So if velocity equals constant, then over here, we've got S equals S initial plus Vt. And then for rotational, we'll have theta equals theta initial plus omega t.